Hello everyone, Marin Mats here. Welcome back to another video. In this video, I'm going to be doing the review for Physics 121 Common Exam number 3. And I apologize for the time at which I'm going to be posting this, as I've been pretty busy last week. I wish you the best of luck. And well, let's get down to this. All right, so I'm going to skip questions 1 and 2 because, well, it's pretty much question 3. All right, it's basically the same application of question 3. So just to save some time, I'm going to do 3 to 16. So for question 3, we have the circuit at right comes to a steady state driven by EMFs. EMF 1, right, is going to be 15 volts. EMF 2 is 6 volts, and they are connected. Okay, just like that. The capacitance, okay, of the capacitor is 6 microfarads, and the resistors are all equal, okay, to each other. So R1 equals R2 equals R3, and all of that is just 200 ohms. Find the magnitude of the charge on either plate of the capacitor at equilibrium. At equilibrium is a keyword over here, okay? Disregard all other writings over here, okay? It's just, you know, somebody else was trying this exam. Anyway, at equilibrium, what happens is that the capacitor gets fully charged, okay? So that's important to know. And after the circuit has been connected for many times constants, right? So after a long time, okay, we're going to find the magnitude of the charge on the capacitors. So it's basically the maximum charge. So we don't have to worry about, okay, the change in charge over time. So we're just, okay, thinking about what's going to happen when the capacitor gets fully charged. So for this circuit, we're going to use Kirchhoff's loop rule, okay, for voltage, which states that the sum of the change in voltage, okay, for a loop, for a closed loop, right, closed loop, is going to be 0. Okay, and that means essentially, okay, if we, let me redraw the circuit somewhere over here. So we have the EMF 1, so we have positive and negative on this side. And then we go down here, we get a capacitor, all right. Then we keep going down, and that's R1. Okay, and then we come down to R3. This is EMF 2, okay, and this is R2. Okay, so what's happening is, well, if you think about it, like somebody pointed out, it's kind of short-circuiting, right? Because we have two EMFs opposing each other. And the problem here is that each of these EMFs will be contributing to charging the capacitor. So let's use Kirchhoff's loop rule, okay, for each of these closed loops. So we have 3 closed loops in total. We have this closed loop over here. We could use Kirchhoff's loop rule in here and here as well, and also for the complete loop, right? So for the entire thing, we can use Kirchhoff's loop rule. So we can come up with 3 different equations for Kirchhoff's loop rule. So for the first one, let's suppose we start, okay, we start at EMF 1, right? So we start over here and then we go in that circular way, in that okay, in that loop. So we start with the sum of the voltages, right? So the sum of the voltages is essentially EMF 1, but because we're going to do the change in voltage, and all of that is going to be equal to 0. So EMF 1 minus, okay, then if we follow the loop, right? If we follow the loop, then we have R3. So that's going to be, in terms of voltage, okay, according to Ohm's law, it's going to be I, right, I3 times R3. And then we have R1 next. So that's going to be minus I1 R1. And then we have the capacitor. And the voltage across the capacitor is going to be Q, okay, divided by the capacitance, the charge over the capacitance. And all of that is equal to 0. That's equation 1. Now let's do the loop rule for, okay, the entire for the entire loop. How about that? Yeah, we could do that. but I think it will be much easier to just do the second loop, right? The smaller one. So this is a smaller loop. So for that, we could start at EMF2. We have EMF2 minus I2 R2 minus Q over C, okay, and then minus I1 R1, okay. All of that is equal to 0, and I think we can already use this system of equations to solve for the charge, because we're trying to look for the charge of the capacitor after a very long time. So now let's take a look at very qualitative aspect of the circuit over here. If we take a look at the first resistor, R1, we can think of it as, after a long time, the capacitor will not have any current flowing through it, meaning that R1 will not have any current, so the voltage will be 0, right, across that resistor after a long time. So we can get rid of these terms over here, and that's pretty useful. So that goes to 0, this goes to 0 as well, and we're left with just, the EMFs and I3 R3 and I2 R2. Now, we are told that R3 and R2 are the same, so we can just, rewrite that as the same. And we can also look at the circuit, and because of the fact that, this resistor R2 is in series with resistor R3, then the current through them will be the same. So we can conclude that, let me move down. We can conclude that these equations will just simplify to, they will simplify to EMF1 minus IR minus Q over C equals 0. And for EMF2, we have minus IR, right? And then minus Q over C. Okay, so if we add both of these equations together, or if we, per se, multiply, we could multiply one of these by a negative, but then we'll get rid of this, we'll get rid of it, right? And that's not what we're looking for. So let's try to use the third loop, so the third loop using Kirchhoff's loop rule. So let's see what happens. So if we use the third loop, we're going to end up with the following. So if we start, per se, at EMF2, we have EMF2 minus I2 R2, and we say that it's going to be the same in this case, so it's going to be I times R, and then we're going to go all the way to EMF1, so that's going to be minus EMF1, and then we have R3, and that's going to be minus IR, right? It's in series, so it's the same current, same resistance, and then that's going to be it. All of that's equal to 0. Okay. Now this is just EMF2 minus EMF1 equals to 2 times IR, right? And if we want to solve for R, if we want to solve for I, we simply solve for it, right? We just divide by 2R on both sides. So we have EMF2 minus EMF1 divided by 2R. Okay, and once we evaluate that, we get that the current is equal to 0.0225. So that's going to be EMF2, the value of EMF2. Let's check what the value is. That's going to be 15 ohms, right? 15 volts. So EMF2 is 15 volts. Let's write it down. So EMF2 is 15 volts, and EMF1 will be 6 volts, right? Yeah, 6 volts. All of that divided by 2 times the resistance, 2 times 200 ohms. That's going to get you to 0.0225. Okay, so that'll be in terms of amps, right? That will be the current. That will be the net current, right? So we're going to use that current, the value of that current, to solve for Q in one of these two equations over here. Okay, so we could choose either of them, right? Either of them works. So let's choose the first one and solve for Q. So if we solve for Q, we know that okay, that's equal to EMF1 minus IR, and then multiplied by the capacitance. So Q is just going to be EMF1. EMF1 is, we said was 15 volts, right? 15 volts, and then minus the current, which we found to be 0.0225, okay? And then multiplied by the resistance, which is 200 ohms. All of that multiplied by the capacitance, which is 6 microfarads. Okay, so the current comes down to be the total current, or the max current should give you 6.67, I believe that's the answer. It's going to be 6.3 times 10 to the power of -7 coulombs. So that's going to be 63 microcoulombs. So this was a relatively long problem for the third question. All right, now let's move on to question number 4. All right, so for question number 4, we have the capacitor in a single loop RC circuit becomes charged to 75% of its final potential difference in 10 seconds. Find the time constant for this circuit. So remember that the time constant for an RC circuit, tau, right, is going to be R times C. So we're looking for tau, or RC. Disregard this over here, okay? So we know that the current function, okay, for a charging capacitor is going to be IT equals to V over R times e to the negative t over tau, the constant that we're looking for. And so we're told that 75%, right, becomes charged. 75% of it, the final potential difference. So of total EMF. The total EMF becomes, okay, charge after 10 seconds. So we're going to look for the time constant. So this is what's going to happen. We could represent 75% as 3/4, right? That's going to be 0.75. So we have that I total, right? I total equals to 0.75 times I total, right? The I total cancels out, and then that's going to be multiplied by negative t over tau. Now, we subtract 1, we subtract, we divide by 0.75, so that's essentially 4/3, and that's equal to e to negative t over tau. Now we ln both sides, so we're going to get that ln of 4/3 equals to negative t over tau. So tau is equal to negative t over ln of 4/3, and that's basically negative 10 seconds over ln of 4/3. That gets you to about 36. Disregard the negative sign since it just tells you the direction of the current. So that's going to be 36 seconds. So that would be answer choice E. Now for question 5, it's a pretty similar question. The sketch advice shows a series circuit, RC circuit, and the applied EMF is equal to 6 volts. The resistance is 200 kilo ohms, the capacitance 5 microfarads, and the switch is initially at position A. The capacitor is charged after a long time when it's at a position A. Then the switch is moved to position B, and the clock is reset to t equals 0. How long does it take for the discharge current, right, very important, discharge current, through the resistor to fall to 30% of the initial value? So essentially, we're going to consider the discharge current, so equation. So, but to do that, we have to look at the equation for charge, right? So the discharging capacitor, the charge for the discharging capacitor as a function of time will be equal to Q max times e to the negative t over RC. And so if we differentiate this equation on both sides, okay, we differentiate with respect to time, we're going to get, okay, that the derivative of Q with respect to time is I, right? That's just current, is equal to, okay, the derivative of e to the negative t over RC. That's just going to give you negative Q max divided by RC multiplied by e to the negative t over RC. Okay, and we know that this expression over here, Q max over RC, is essentially the initial value for the current. So the function, okay, the current function for the discharging capacitor will be equal to negative, well, the negative just describes the direction of the current. So that would just be I initial times e to the negative t over RC. Now we're going to solve for the time constant, right? So they're asking how long does it take, right, for the discharge current to for the resistor to fall 30% of its initial value. So we're looking for T, and we're given R, we're given C, and so we know that I max, okay, has to be 30%, right? So we're going to look at this. So the total current will be 30% of the initial current. So we're going to multiply 0.30. So that will be 0.30 times the initial value, which will be our our final current. That's going to be equal to the initial current times e to the negative t over RC. The current cancels out, then we ln both sides. So that's going to give you negative t over RC equals to ln of 0.3. And so t is going to be ln of 0.3 multiplied by RC times -1, so negative of that. And so it's going to be negative ln of 0.3 times 200 kilo ohms, right, multiplied by the capacitance. And the capacitance is 5 microfarads. Okay, so that's going to be 5 microfarads. Oh boy. Okay, 5 microfarads. Okay. And so once you solve for that, you're going to get that t is equal to 1.2 seconds. Okay, approximately. And that's going to be answer choice B. Okay, right over here. Now let's move on to question 6. An electron moves within a uniform magnetic field. Its instantaneous velocity is v equals to, okay, vy j hat plus vz k hat, where vy is 4 meters per second and vz is 2 meters per second. So we could just rewrite it as, okay, the vector v equals to 4 j hat and then plus 2 k hat, okay? And then the field is given by v. B is equal to bx I hat plus vy j hat, and bx is 2 teslas and by is 4 teslas. So we have 2, okay, I hat plus 4 j hat, okay? And so the charge on the electron is negative 1.6 times 10 to the negative 19 coulombs, and well, that's a commonly known fact, hopefully. And so we're going to find the force F exerted on the electron by the magnetic field. And so remember that the force, okay, is equal to QV cross B, right? So the cross product of the velocity and the magnetic field times the magnitude of the charge. So we're going to find the cross product between these two vectors given the components of each. So in order to do that, we're going to find the determinant. That's what they call it, okay, in the matrix world. So let's lay out the matrix over here. So we have V, we want to cross V onto V, so that's going to be V, and then this is going to be B. So we're going to make a 3 by 3 matrix. So that will be the I hat component over here. This is the J hat component and the K hat component. Over here for V, we have 0 for I hat, right? We have a 0 J I hat component. We have 4 for J hat, and we have 2 for K hat. Now for B, we have 2, okay? We have 2 for I hat, 0 for J hat. Oh no, my apologies. We have 4 for J hat. 4, and then we have 0 for K hat. Okay, now we're going to find the cross product. So the cross product, so F will be equal to Q times the cross product, which in this case will be 0 minus 8, okay, I hat. And then we'll have minus 0, and then minus 4 J hat, and then we have plus, okay, the cross product over here for the K component will be 0 minus 8 K hat. So we simplify all of this and we add Q to the equation, the magnitude of Q. Then we have negative 1.6 times 10 to the negative 13 coulombs multiplied by negative 8 I hat plus 4 J hat minus 8 K hat. And the answer choices are not similar to this, although all you have to do is basically factor out 8, excuse me. So you factor out an 8 from the cross product over here. So if you factor out an 8, or a negative 8 more, to be more specific, you're going to get the following. So you're going to get F equals to 1.6 times 8, right? Times 10 to the power of negative 13. And then you're going to get I hat, okay, minus 0.5 J hat, and then plus K hat. Okay, and so you're going to get that the force is going to be about 1.28 times 10 to the power of negative 18 times I hat minus 0.5 J hat, and then plus K hat, which is essentially answer choice E. Okay, so they just factor out negative 8, that's all. Now for question 7, a wire whose length L equals 4 centimeters is placed under a uniform magnetic field of magnitude B equals 0.5 teslas, which points into the page. The wire carries a 3 amp current to the right in the plane of the page. What are the magnitude and direction of the force exerted on the wire by the magnetic field? And well, it was already solved over here, so we have that the force is I, and then the cross product, okay, of L and B. So filled, pretty much, right? That's what my teacher used to call it back then in the all good days of high school. Now F equals I, right? In this case, it's given, it's 3 amps times L, which is 0.04 meters, okay, and then times B, which is 0.5 teslas, and that's going to be 0.06 newtons. And well, where is it going? We're trying to look for the direction of the force, right? So we have this wire, and then the current is in this direction. Now, the magnitude of the magnetic field, or the direction of the magnetic field is into the page. So if you use the right-hand rule, right, then you're going to end up getting that the force is up. Okay, it's going up. The magnetic force is up according to the right-hand rule. Okay, since the cross product of I and B is going to be up, right? All right, so it's going to be answer choice A. Now for question 8, let me move this a little bit so it's clear. We're going to suppose that we need to build a velocity filter using crossed electric and magnetic fields to select one speed for which charged particles in a beam pass through the fields without being deflected. What value of the electric field E should be used in such a device to select 5,000 electron volt protons if the magnetic field V is fixed at 4 teslas? The mass of a proton is 1.67 times 10 to the negative 27 kilograms. Okay, so basically this is a velocity selector problem, and what we have here is two plates, right? We have a potential difference over here, and this is positively charged. Okay, this is positively charged, and then we have another plate which is negatively charged. It's basically a capacitor, and the electric field's direction is going to be from positive to negative, right? So it goes from positive to negative. Okay, so that's going to be the electric field. Now the magnetic field goes into the page, right? So the magnetic field, okay, goes into the page. And what else do we have here? So we have to imagine, okay, that we have a proton over here, and we're going to find, okay, the value of the electric field in such a way that, okay, we can achieve 5,000 electron volts, right? And that's a measurement of energy, right? We know that we could find the velocity required, right? The velocity that we're looking for. So if we know the velocity that we're looking for, and we know the magnetic field's magnitude, then we can find the electric field's magnitude. Okay, so what's going to happen over here is the velocity will be in the upward direction, right? This is V, and now the electric field will always go towards the negative charge because it's a proton. Protons are positively charged, so they get attracted to the negative charges. So it goes in this direction. This is the electric force. Now the magnetic force, you have to use the right-hand rule. So the velocity is your index finger, and then the magnetic field points into the page, so the magnetic force will be to the left. And we want that to be equal and opposite to the electric force. Alright, so we know that the electric force B is QVB, right? Magnitude of the charge times velocity times the magnetic field. And the electric field, okay, force is going to be QE, Q times the electric field. At this point, we know that if the electric force and the magnetic force are equal, then QVB equals to QE. The Q's cancel out, and so if we're trying to look for the electric field, that's just going to be the velocity times the magnitude of the magnetic field. Now, we're given a unit of electron volts, and we want to convert that into joules so we can find the magnitude of the velocity. So we know that 1 electron volt, 1 eV, is going to be equal to, okay, 1.602 times 10 to the power of negative 19 joules. That's the value of 1 electron volt. So we can use unit analysis to find out what's the value, okay, of 5,000 electron volts in joules. So 5,000, we have 5,000 electron volts, and then we multiply by 1.602 times 10 to the power of negative 19 joules per 1 electron volt. The electron volt unit cancels out, okay, and we find what the value of this is in joules, okay. So once we do that, we can find the magnitude of the velocity, okay. So that's going to be equivalent to 8.01 times 10 to the power of negative 16. Okay. Now, we want to find the velocity, right? So that's going to be 1/2 mv squared equals to the energy. And this is the energy. Energy is 8.01 times 10 to negative 16 joules. So the velocity is equal to 2 times the energy divided by the mass, and then to the power 1/2. Okay, the square root of 2e over m. And so if we plug our values in to this equation, we plug our values into the equation, okay, we get that V equals to the square root of 2 times 8.01 times 10 to the negative 16 joules divided by the mass of the proton, which is given as well, and the mass of the proton is 1.67 times 10 to the power negative 27 kilograms. Okay, and so the velocity, okay, the velocity will be, let's see what the value of the velocity is. I think I didn't quite, yeah, it's going to be 9.8 times 10 to the power of 5 meters per second. That's the velocity. But we're looking for the electric field. Now that we know the velocity that we're trying to get, and we know the magnitude of the magnetic field, which is uniform, then we can find the electric field. So the electric field is equal to velocity times magnetic field, so that's 9.8 times 10 to the power of 5, okay, and then times 4 Teslas. All of that will be equal to 3.9 times 10 to the power of 5, okay, and the units for electric field will be, it could be joules, meters per second times Tesla, right? Meters per second times Tesla, or volts per meter. So either way works, and that will be answer choice D. Okay, so for question 9, okay, we have, let me redraw this image. Okay, so it's going to be something like this. Okay, we have a loop over here, and then we have a smaller loop, A. We got a current carrying wire, okay, into the page. I3, we got this. This is loop D, the bigger loop. Then we got something like this. This is called C. We got a current carrying wire into the page, I2. And we got another loop, and then there is a current carrying wire, I1, out of the page. I'm sorry, the other way around. This is into the page, this is out of the page, the I2 and I3. Okay, and this is loop B. Okay, so now the figure shows, okay, in cross-section 3 conductors that carry currents perpendicular to the plane of the figure. If the currents I1, I2, and I3 all have the same magnitude, okay, they're all equal, for which of the following paths shown is the line integral of the magnetic field equal to 0? So the line integral of the magnetic field is basically, okay, Ampere's law. And Ampere's law, okay, so it's going to be integral of the magnetic field, okay, around a closed loop. So that's going to be equal to mu0 times the enclosed charge, the enclosed current, right? So we're trying to see where the enclosed current is 0. And well, the first one that's pretty obvious is A, right? There's no current enclosed in the loop of A. So A is one of the answers, right? Because the enclosed charge is 0. Now, if we look at D, right, the bigger loop, well, there will be a net. There will be a net current, right? Two of them will cancel out, but then there will still be one left. Now, C is obviously going to cancel out because they're equal and opposite. So C and A are the right answers. So paths A and C, which is answer choice B. For question 10, okay, the sketch shows a cross-section of 3 parallel wires, each carrying a current of 15 amps. The currents in wires B and C are out of the page, while that in wire A is into the page. The distance R equals 10 millimeters, okay? And what is the magnitude of the force per unit length on wire B? Okay, so, well, we know that, okay, we know that the magnitude of the magnetic field, right, about a current carrying wire, it's going to be mu 0 I divided by 2 pi r, right? Okay, 2 pi r, meaning r the distance from the current carrying wire. And so we're trying to find the magnitude of the force per unit length. So we know that the force, right, the force of one wire is equal to the current through that wire, okay, times the length, times the magnetic field of the second wire, right? So it's basically the force due to, okay, the force on 1 due to 2, okay, because of the magnetic field of wire 2. All right, so we have to substitute over here, supposing that this is the magnetic field for the second wire. We substitute that into this equation and we get that F1 equals to I1 times L and then multiply by mu 0 I2, right, this is I2, divided by 2 pi times R. Okay, so it's essentially like this, I1, I2, mu 0, and then divided by 2 pi, and then the distance. Okay. Now, I dismissed the L. So if we want to find the force per unit length, we divide by L on both sides, and we get that nice equation. So that's the one equation we're going to be using. Now, because we have 3 wires, okay, we have to use 2 different expressions for force. The force on wire B, right? So, excuse me, essentially what we're going to do is the following. So, we're going to find the force on B due to A and C. So, the net force, okay, the net force, force net, equals the force on B, okay, the force of A onto B plus the force of C onto B. Okay, and we can say that these are both going towards the same direction because, okay, we look at it. We can say that the magnetic field, okay, using the right hand rule, right, the thumb rule, to find the magnetic field direction onto B. So let's do it for A, right? So if it's going into the page, the magnetic field lines will be concentric, right, like that. So eventually we'll hit B like that. So it will be in the down direction, right? Meaning that the direction of the force, since the current is coming out of the page, right, and the magnetic field is down, okay, the force will be to the right. So the electric force, the magnetic force of A onto B will be to the right. So this is F, A of A onto B. And the same goes for, okay, the force of C onto B, because if you think about it, okay, the direction of the magnetic field of C onto B will be the same, right? It will be something like that. So the tangential direction over here is down, and we have that the force is well in the same direction, so it will just be F C onto B. Okay. Now the only concern here is that we have different distances, right? We have distance. Oh, this actually erases the whole thing. Okay. Well, let's undo. All right. Well, we have the distance from A to B equals to 3r, right? And from B to C equals to r. All right. That's all we need to know. Now we just use the force per unit length equation to find the net force. So the net force equals the force of A onto B, which will be, okay, let's remember that all the currents are the same, right? So we have the currents in wire B and wire A are the same, right? So we have I, okay, we have I squared, right? We have I squared, and then mu 0 divided by 2 pi, and then times whatever the distance is between A and B, which is 3r. Okay, so that will be it. And let's see what we have now. So then we're going to have that this is going to be added to the force of C onto B, and the force of C onto B is going to be, okay, the same. Okay, it's going to be I squared mu 0 divided by 2 pi times the distance between B and C, which is just R. Okay, so what's going to happen now is, well, essentially we simply multiply. Okay, we simply substitute our values in here. So we have that because the current is the same. Okay, then we have 15 squared, and then times 4 pi times 10 to the power of negative 7 divided by 2 pi, okay, times 3 times 10 millimeters, and 10 millimeters is 10 times 10 to the power of negative 3 meters, and then plus 15 squared, and then 4 pi, okay, 4 pi times 10 to the negative 7, all of that divided by 2 pi times 10 millimeters, or 10 times 10 to the negative 3. Now we plug this into our calculator. Now let's see what we get. Okay, so let's see what we get if we plug this into our calculator. Okay, so we have 15 squared. We can factor out 15 squared times mu 0. So 15 squared, and then multiply by 4 times pi. Okay, 4 times pi times 10 to the power of negative 7. Okay, so factor that out, and then we have 1 divided by 2 pi, okay, times 3, and then times 10 times 10 to the power of negative 3, and then plus 1 over, okay, 1 over 2 times pi times 10 to the power of negative 3. Okay, so when we get that the magnitude of the net force, okay, net force equals to 0.006 newtons. Okay, the force per unit length is going to be newtons per meter. Okay, so that would be answer choice C over here. Okay, all right, so that would be the force per unit length on wire B. Let's go to question 11. Now this one is actually an easy question, so let's see. Two positive point charges move side by side in the same direction with the same velocity. So they are both the same charge. What is the direction of the magnetic field that the upper point charge exerts on the lower one? Now let's see what's the direction of the magnetic field of the upper point charge. So we use the thumb rule. Okay, so the thumb rule, and then the thumb is, well, the velocity. So that means that the magnetic field will be, okay, we curl our fingers, they'll be into the page. So that'll be into the page over here, the magnetic field. So if we use the right hand rule, right, we can find that the force, right, the force will be up, right? The magnetic field force will be up. So it's basically an attractive force. So it's the answer choice E. All right, question 12. Now, if A is 4 centimeters, B 12 centimeters, and the current I equals 20 amps, what is the magnitude of the magnetic field at point P, the center of curvature of the arc segments? Okay, so for this question, we're going to use the fact that the magnetic field, okay, due to an arc, okay, is going to be equal to mu 0 I divided by 4 pi. Okay, I'm sorry, not 4 pi. It's mu 0 I divided by 4 times the distance. Okay, so it's times 4 times the distance r, right? Okay. So we want to find out what's the magnitude of the electric field at point P, which is the center, right there. But now we have to think about the fact that each curve, right, each arc has a different direction for the current, right? So if we look at the first, the lower curve, right, the lower arc, the direction of the current, okay, is counterclockwise, meaning that the direction of the magnetic field at point P, okay, will be out of the page. Will be out of the page. And so we can look at the second curve now, the second arc, and because the direction of the current is clockwise, then the magnetic field will be into the page. Okay, will be into the page, but now you could argue that, well, it might be with less magnitude, right? The magnitude is less, and that's because, well, the current is the same for both, and the distance is greater, so it makes sense that it will be less, right? The magnitude of the magnetic field. So to find the net, okay, the net magnetic field, B net, we have to subtract the magnetic field due to the smaller arc minus the magnetic field due to the larger arc. So that's basically mu 0I divided by 4 times the distance, okay, A, minus mu 0I over 4 times B. Okay, we factor out mu 0I, B net equals to mu 0I times, okay, 1 over 4, 1 over A minus 1 over B. Then we substitute our values and we get that this is going to be 4 pi times 10 to the power of negative 7 multiplied by the current, which is 20 amps, okay, divided by 4 times 1 over A, and A is 4 centimeters, which is 0.04 meters, and then minus 1 over 12 centimeters, which is 0.12 meters. Okay, so that will give you about 0.1 micro Teslas. Okay, that's answer choice C. All right, let's move on to question 13. Okay, so 4 parallel conductors all carry equal currents of I equals 6 amps. The sketch is an end view of the conductors located at the corners of a square whose edge is L 0.50 meters. Current flows out of the sketch at A and C and D and flows into the sketch at B. Find the magnitude and direction of the magnetic field at point P, the center of the square. Well, let's see. So the distance, okay, the distance over here, this whole distance will be equal to L times the square root of 2, right? And so we divide that distance into 2. We're going to get L square root of 2 over 2. Okay, so that will be the distance between each, okay, between the center and each of the current carrying wires. So we can take advantage of that, and we can use the fact that the magnetic field, right, the magnetic field due to a current carrying wire is equal to mu 0 I, okay, divided by 2 pi, and then times the distance, right? Okay. Now let's figure out in which direction each magnetic field is going to. So let's see, for current carrying wire A, if we use the thumb rule, well, we have that. Let me actually draw it over here. We have A, which is coming out of the page, and we have C over here. It's coming out of the page as well. D, okay, coming out, and B into the page. Trying to find what's going on at the center, right? Now for A, well, we have to use the right-hand rule, right? And we know that it's going to be concentric, so it will be in the counterclockwise direction, meaning that at the center it will be kind of tangential, so like that. This will be the direction of BA, right? Now for the current carrying wire C, it's going to be tangential in this direction, okay? So because it's going to be counterclockwise as well. Okay, so that will be BC. Now for D will be the same rationale, so it will be BC in this direction. And now for B, right, VB, we're going to have to use, okay, the thumb rule, but into the page, right? So that's going to be actually in this direction. And look at that. BA and BC cancel out because they're equal and opposite. And we have that BC and BD, well, they're in the same direction, right? Well, that's good. All right, so we can add both of these. And we can say that because they're identical, well, that's just 2 times as much, right? So B net, right? B net is equal to 2 times, okay, 2 times B, which is 2 times mu 0 I divided by 2 pi. D, the 2 cancels. We know that that's going to be mu 0 times the current, which is 6 amps, divided by pi, multiplied by the distance, which is L square root of 2 over 2. And L is, well, going to be, let me actually write that out completely. So the magnitude of the magnetic field, okay, will be 4 pi times 10 to the power of negative 7 multiplied by 6 divided by pi times L, which is 0.5, right? 0.5 meters, root 2 over 2. And then once you plug that into your calculator, you're going to get that's about 6.8 times 10 to the power of negative 6 Teslas. And of course, the direction is going to be towards D. Okay, so that's answer choice D. Okay. Now for question 14, a circular wire loop having a 10 centimeter radius is carrying a current of 200 milliamps. I'm going to skip this question, actually, yeah, because I didn't go over this. So let's skip this question for now. Now question 15, okay, so for question 15, we have that a circular loop of wire with radius R equals 10 centimeters carries a current of I equals 8 amps, as shown in the sketch. The wire lies in the plane of the paper, with long straight parts along the x-axis. Find the magnitude and direction of the magnetic field created at the center of the loop. Okay, so at the center of the loop, we're going to have a magnetic field due by the wire, right, and by the current carrying wire, by the loop, and by the current carrying wire. So basically, the net magnetic field, right, is going to be mu 0 I divided by 2 pi r plus mu 0 I divided by 2r, right? While when this over here is the magnetic field due by the current carrying wire, the stray wire, and this is the loop. So, okay, we know that B net, okay, is just equal to 4 times 10 to the power, 4 pi times 10 to the power negative 7 multiplied by the current, which is 8. Okay, current is the same, right? And we're adding them together because we know that the direction will be the same, right? If you use the thumb rule, right, you're gonna find out that the magnetic field will be like that, will be concentric, okay, and then it will be out of the page. So, and the same goes for for the current carrying wire. It goes like that, and so the direction at the center will be out of the page. So it will be in the same direction. Okay, and then this all of that multiplied by 1/2 times pi r, and r is basically 10 centimeters, which is 0.1 meters, plus 1/2 times 0.1. So the magnitude of the net magnetic field is going to be 6.63 times 10 to the negative 5 Teslas. And it's out of the page, like we discussed over here. Okay, so it will be answer choice B. Now, last question. This one is interesting. Okay, so over here we have a long conducting cylinder that has outer radius A equals 8 centimeters. A cylindrical cavity within it has radius B equals 4 centimeters, as shown in the cross-section sketch. The conductor carries a total current of 3 amps, which is uniformly distributed over the cross-section of the conductor. Current density is constant. That's important. What is the magnitude of the magnetic field due to the current in the wire at a radial distance of r equals 6 centimeters from the central axis, a point inside the conducting portion of the wire? Okay, now how would we start this problem? Well, first of all, okay, we have to lay out, we have to know what's the magnitude of the magnetic field, okay, according to Ampere's law, right? So we need to know what's going to be the magnitude of the magnetic field. So we know that the closed loop integral of the magnetic field dot ds will be equal to mu0 times the enclosed current. Okay. Now, if we consider the entire wire, right? If we consider the entire conducting cylinder, we know that B is a constant. And that's going to be the integral of ds, which will be 2 pi times the radial distance, okay, total radial distance, which is A, and that's equal to mu0 I enclosed. So the magnetic field will be mu0 I enclosed divided by 2 pi times A, okay, and this is for r is greater than or equal to A. Good. Now, we need to take advantage of the fact that there's a cavity over here, so we need to tackle that problem. So in order to do that, we can use a ratio of the cross section of the areas, okay, where the current is actually coming from, right? So where the current is included, right, which is only in this portion of the conducting cylinder. So we can say that the current I prime, right, the new current, because we're going to find the magnitude of the magnetic field at halfway between B and A. So basically we're going to find this using Ampere's law. Now we need to know what's the enclosed current, the new enclosed current, I prime. Okay, we know the total current, that's I, and we can find it. Okay, we can find it using the original equation, right, for for this over here. That'll be the enclosed current. But we're talking about cross-sectional areas, right? We're going to do ratios of cross-sectional areas. So the new enclosed current will be equal to, in cross-sectional area, it's going to be equal to pi, right, times, in this case, the outer radius will be r, right? So that'll be r squared. And the inner radius will be b, so minus b squared. That'll be the cross-sectional area of the new current. The cross-sectional area of the total current is going to be pi times a squared minus b squared, right? A squared, a is the outer radius and b is the inner radius. So if we find the ratios, okay, the ratio of the new current over the old current, the total current, we know that's going to be pi r squared minus b squared divided by pi a squared minus b squared. The pi's cancel out, okay, and we can use this to find the the new current in terms of the total current. I prime equals to R squared minus B squared divided by A squared minus B squared times the total current. Okay. Now, given that we found I prime, we can use Ampere's law in order to find the magnitude of the magnetic field at the radial distance r, which is 6 centimeters. So we have the closed loop integral, right? The closed loop integral of b dot ds equals to mu 0 I prime enclosed. I prime in terms of I will be this over here, right? So that's equal to mu 0 times r squared minus b squared divided by a squared minus b squared, and then times I. Okay, we know that the integral of ds along this loop will be 2 pi times the radial distance r. So that will be b as constant, taken out of the integral, and then we have 2 pi times r. Okay, that's equal to mu 0, and then r squared minus b squared divided by a squared minus b squared times the original current, I, the total current. Okay, so now we have that the magnitude of the magnetic field, right, B, okay, at a radial distance r will be equal to mu 0 divided by mu 0 right, divided by 2 pi r, and then times r squared minus b squared divided by a squared minus b squared. And let's plug in the values. Okay, so we know that b is equal to 4 pi times 10 to the power of negative 7 times the current, okay, which will be 3 amps, and then divided by 2 pi times the radial distance r, which is 0.06 meters, right? 6 centimeters is 0.06 meters. And then we have r squared, so 0.06 squared minus b squared, so that will be 0.04 squared divided by a squared minus b squared, so that's going to be 0.08 squared minus 0.04 squared. Okay, so that should give you a value that is about 4.2 micro teslas. Okay, so that should be the magnitude of the magnetic field at the radial distance r. Okay, so this is for r. Okay, r is greater than or equal to r. Okay, so that's going to be answer choice C, I believe. Yeah, there you go. All right. Well, that wasn't too bad. Okay. Well, that's it for today. I wish you the best of luck on tomorrow's test, and make sure you review your formulas and understand how they work, especially Ampere's law and why it works. That's important to know. Thanks for watching. I hope you found this video useful, and I'll see you next time. Thank you.